Thank you. So the next paper is Radio2Text, streaming speech recognition using mmWave radio signal. The presenter is Zhao from University of Hong Kong. He's looking for collaborators for anyone who is interested in sensor-based human-machine interaction.
Thanks for the introduction. Hello, everyone. I'm Zhao. I'm glad to share our paper Radio2Text here. First, I will introduce the background of the radio frequency microphone or radar microphone. In our life, microphone is a widely used sensor to record speech for subsequent speech recognition, just like the smart speaker. However, microphone can now discriminate ambient noise or irrelevant audio, and soundproof materials will hinder the propagation of speech waveform. Therefore, microphone fails in noisy and soundproof scenarios. Compared with microphones, the radio frequency-based automatic speech recognition system is able to deal with these issues. The basic idea of RF microphone is to realize the conversion from radio signal to audio signal through the medium of vibration. Most importantly, RF signals are insensitive to ambient noise and can traverse occlusions. Therefore, RF-based microphone can still work well in noisy and soundproof scenarios. In real applications, latency and the size of recognizable vocabulary size directly influences the effectiveness and efficiency. Therefore, it is desirable to achieve streaming speech recognition on text with a large vocabulary. Existing solutions neglect such potential requirements. They do not support streaming mode, and they can only recognize a few words or commands. So we propose the Radio2Text system. In a nutshell, Radio2Text can accurately recognize the text containing a vocabulary of over 13,000 words in a low latency streaming mode, even in noisy and soundproof scenarios. To achieve the goal of our implementing Radio2Text, we need to address two challenges. The first one arises from the aspect of streaming as a network. Increasing the recognizable vocabulary size results in more potential matches for the given input radio signals, which increases the possibility of ambiguity in recognition. Restricted by the streaming setting, streaming SR networks can only rely on historical information without incorporating entire future information for prediction. These factors result in inferior performance compared to non-streaming networks with small vocabulary size. The second challenge is associated with the inherent attributes of RF signals. Restricted by the design of radar, the upper frequency that radar can perceive is limited. Missing high frequency band compromises the integrity of speech information. Moreover, reflected millimeter wave signals are likely to be flooded by the noise due to the weak vibration amplitude and the attenuation of the reflected millimeter wave signals. These factors result in a degradation in the quality of input speech-related millimeter wave signals and further affects the performance. To overcome these two challenges, we designed Radio2Text as this structure. It mainly includes three components: streaming transformer, guidance initialization, and cross-model knowledge distillation, and we will detail them below. Given the first challenge, the backbone network possessing powerful feature representation ability is the basis for streaming SR with a large vocabulary. Therefore, the encoder-decoder-based transformer is selected as the backbone as it can effectively extract features and adaptively construct relations with the context. To implement streaming setting, chunk-wise setting and triggered attention are integrated to the transformer. To alleviate the deficiency of the streaming network unable to access entire information, guidance initialization is proposed to enable the streaming transformer inherits the feature knowledge that is relevant to the global context. Specifically, guidance initialization uses the trained weights of the selected layer of the non-streaming transformer to initialize the corresponding layers of the non-streaming streaming transformer. For the second challenge, fortunately, The paired speech signals share the same information representation and target with mmWave signals, and the paired speech signals contain sufficient and accurate acoustic features. This provides a new angle to tackle the negative effect of low-quality mmWave signals. The cross-modal knowledge distillation is proposed to transfer the knowledge from the audio transformer to the radio transformer in feature and responses level through knowledge distillation. While I present experimental results, we first conduct our experiments in query scenarios. We use the TR radar to collect RF signals, and the loudspeaker is used as a speech source. Moreover, we may consider two potential application scenarios, including eavesdropping and conference speech transcription. We provide some examples decoded by Radio2Text to visualize the results. It is obvious that a sentence containing many distinct words are correctly recognized from here, and we especially select certain representative misrecognized sentences for reference, just listed here. Misrecognized words or characters are very close to the ground truth, and the incorrect character words are normally articles which do not affect the understanding of sentences. The quantitative evaluations are conducted at two distances, that is 50 centimeters and 150 centimeters, which correspond to these two potential applications. These results validate the effectiveness of Radio2Text in streaming speech recognition on large vocabulary. We also compare our Radio2Text with other methods. It should be noted that other mmWave-based methods are compared for non-streaming recognition, as they do not support streaming mode. Actually, it is unfair to our method, but the results show that Radio2Text is on par with the microphone-based method in terms of average and surpasses other mmWave-based methods. We also consider the complex scenarios, including noisy and soundproof scenarios. In noisy scenarios, the microphone-based streaming SR method almost fails here. And in contrast, a mmWave-based method still maintains a similar performance to that in query scenario. And Radio2Text achieves the best performance. In the soundproof scenarios, despite a decrease in performance, Radio2Text still achieves the lowest error rate among all streaming and non-streaming methods. Moreover, we also perform some evaluation studies to validate the effectiveness of each component of Radio2Text. Finally, we also analyze the robustness of the Radio2Text on the different distance, radar direct orientations, volume levels, and environmental changes. Yeah, thank you. And if you are interested in our paper, you can also check out the website for our related works. Thank you.
Thank you. Any questions? Okay, so I have a question, of course. So can you talk a little bit more about the system? How do you envision your system will be used in the future? Right now, I understand that it's a prototype. What scenario are we going to deploy system to be used in the future?
Yeah, as I mentioned, the potential application scenarios include eavesdropping for privacy and security, and conference speech transcription, just like this screen. Yeah.
Great, thank you. All right, thanks, speaker, again. Okay, so we'll have the next paper is also a mode paper. It's Smart Side Pad, a smart seat pad for cycling fitness tracking, leveraging low-cost conductive fabric sensors. The